Ready?
evening, ladies and gentlemen. We're here to talk about our RASC-AL competition team, Serenity.
This is a NASA competition for university students. The goal of the competition is actually to create a rover for space exploration, which recognizes and picks up small multicolored pebbles on a simulated non-Earth landscape.
This competition is slated for June 2015 in Houston, Texas, but more on that later.
These are our current team members. Our team leads are Alexis Palliser and Alex Rosendale, and our system leads are Mark and Lewis with an asterisk. The Taylor Squad is our mechanical team lead, Eve Durand is our programming team lead, and Bennett Torrance is our electrical team lead. Everyone in our teams can shift roles in our team's other systems.
Our project objective is to create a viable rover for the RASC-AL competition in Houston, Texas. This means it has to negotiate various environments while continuing to collect small colored rocks.
Our short-term goal, however, is to make sure that this rover can move. So we're going to be a short-wave radio helping us get it deployed.
Our long-term goal is to have a sensory system incorporated into our mobile setup and have it able to recognize colored rocks as well as sample density of target environments.
Our team is using previous classes designed for the same competition. A track design using a skid-steered system.
This was decided to streamline the design process and allow us to save money in the process by building off previous work.
All right, this is our current design for our track system. It essentially uses a metal belt linkage and a drive motor, as you can see at the top. And the track itself is actually a stiff system, so that entire suspension is stiff and fixed. It doesn't move around, and this actually allows the rover body to remain pretty level, and also it maintains tension in the link belt.
This allows for a lower or higher performance, lowers ground pressure, and makes it easier to navigate this terrain.
Alright, this is the current design of the suspension system of the rover we inherited. This design is similar to a rocker bogie, and it allows the rover body to remain more level while reversing.
All right. The current design, as it stands, needs augmenting in the swing arm at the top, as you can see there. It's also highlighted in that rather lousy picture, unfortunately, of the Curiosity rover. And basically, we need to augment it, beef it up a little bit, and enable it to traverse much larger obstacles than it can already do. So.
Okay, so this is our current camera mast design. It allows a higher vantage point, and we have yet to determine exactly how many cameras and sensors are going to be mounted to the camera mast.
We also chose this design because it's similar to sensor masts on other Mars rovers.
Using this design will help us attain the stope size requirements specified by the competition rules.
All right, our current mechanical design is using the track system as shown. Not shown.
Oh yeah, it was shown,
right one?
shown previously, sorry.
We will be modifying the suspension by increasing the bar size and augmenting the hinges on the suspension struts of the track.
We are using previous analysis of the current design to optimize the suspension for development versus.
And our current robotic arm is still not pictured here tonight, but it will be a soft silicone beak-like structure for the grabbing part. Now, the reason we chose a beak-like structure is because the small pointed end of the beak can actually pick at the smaller sample sizes, which are around 1 to 2 centimeters in diameter. And then if for larger samples, we can actually grab at it with about an 8 centimeter size. So it's very robust and it can actually be size modifiable for this. And the robotic arm it's going to be attached to will be a 3 degree of freedom, a very simple robotic arm, so we don't have to work with too many servo motors and things like that. And basically the robotic arm will fold and stow beneath the rover chassis just for storage. Okay.
The electrical team is currently specifying what they need and why. We are mostly focused on the movement systems and power distribution.
The electrical team is currently focused on power distribution, as competition rules prohibit charging. We are looking at the use of solar cells on the rover to conserve battery power.
The battery system we've decided on will be a lithium-ion battery system chosen for its stability as well as power density.
The communications will first be done through a Spectrum DX8 for initial motor control, and later will be conducted through a 2.4 gigahertz antenna and laptop, along with backups using an RFD900 architecture.
Our guidance system right now is a combination of an IMU, so it's an inertial measurement unit. It's a 9-degree of freedom system, which has an internal compass essentially, and it also measures rate gyro and also just accelerometer effects. And we also will have a GPS system linked in to our guidance system. And essentially this is going to keep the rover on a specific course during the competition. Then the computer, while we're moving through the course, will automatically correct for any errors that might be introduced, such as obstacles, through the course of the rover.
The programming team has chosen to use C++ or Java since most of our computing power will be coming from an Arduino. Eventually, we'll use a Raspberry Pi for the color recognition algorithms, and these were chosen for their low cost to computing power.
The programming team is currently being acquainted with programming C++ to be able to program extremely fast using open source compilers for cost effective.
All right, our current project plan is to move the Artemis II rover, which is the previous class, the 466 team that they have built, from nuclear engineering, to, like the nuclear engineering building where it's at right now, to the How Make to Innovate lab. So we can actually begin work on it immediately. It still hasn't been done yet. Go ahead.
While we have the rover in the lab, the 466 class will work with us to optimize the suspension, but we'll first put on a new rocker swing arm to make it highly resistant to strain.
While we have in the lab, we will install electrical systems and begin the program experiment routines into the rover as a parts list for each system.
Our goal is to be able to negotiate the largest obstacles specified by competition rules, those obstacles being rocks about 10 centimeters. 10 centimeters, yeah, in diameter.
This is our current timeline. A couple events worth noting right now are the 24th of October, and this is when we find out whether or not we've actually been at, whether or not we're competitive for the RASC-AL event. The rest of the time I will continue regardless of whether or not we actually get into the event, but this is a significant point in our timeline. By the end of November, we actually hope to be driving the rover around, as you can see here.
And by the end of the semester, we plan to have fully functional and optimal as a rover. This project is slated to take 2 semesters. We'll definitely be able to make a project as well. This was a robotic competition.
Our budget is more or less contingent on whether or not we make it into the competition. If we do, we'll have up to $10,000 in total to spend on the rover development. If not, we'll have a lot less, and we'll have to allocate resources for our rover a little more sparsely. This meaning only $50 for the costs of microcontrollers and programming software, $1,000 for total costs of electrical systems, and around $3,000 for our mechanical systems.
In conclusion, what we really are waiting for is hearing back from the National Institute of Aerospace, and that'll help us really design out our budget right now. And essentially, we'll know which one we should plan for.
This project is scheduled to take at least 2 weeks, but we can take more time if needed for future improvements to our design and entering into
Semesters.
Yes.
This will also increase the university's national competitive presence, and it'll help get more students interested in science engineering through kind of a marketing campaign. And basically, we're trying to interest all students across all fields of study in science on a cultural level.